Welcome back. In this video, we are going to look at linear regression using the TensorFlow core APIs. In the previous video, we looked at the logistic regression again using the core APIs, and this is with linear regression. We won't be going into the theory, but this is the model that we'll be using, and this is the loss function, that is the mean squared error loss that we will be using while coding. And once again, this particular code is available at this link posted in the also in description. This is the TensorFlow docs, and I'll be simply copying the code from the docs and explaining as we go. So the very first thing we need is the libraries, and for libraries, let's see what we can find. So setup, we have the TensorFlow library, import TensorFlow as tf, import pandas as pd, import matplotlib.pyplot as plt, and we also want to import matplotlib, and we can print TensorFlow version as follows: tf dot underscore underscore version underscore underscore, and finally we'll set the random seed, set random seed, and this we'll set by using tf dot random dot set underscore seed 22. And the data set that we'll be using for this particular video is the auto MPG dataset. And there's a previous video in the same series with this exact same dataset, which was based on using the Keras utilities. And here we are going to use just the TensorFlow methods or APIs. Now to load the next step for us is to load and pre-process the data. So let's create a heading for that. Load and pre-process the data. For this, the URL at which the data set is available is as follows: http://archive.ics.uci.edu/ml/machine-learning-databases and auto-mpg, and then we have auto-mpg.data. So that's the URL we have. And next, well, let's look at the column names that we'll be using for this data set. Column names is equal to mpg, and then we have cylinders, and then we have displacement. So these are all the features available that we are going to use to predict the miles per gallon for any vehicle. So given the weight and type of engine, we should be able to predict the miles per gallon. Acceleration, model year with a capital Y, and finally we have the origin. Okay, so with this, then we can now use the pd.read CSV, and we'll put the CSV in this particular data frame called dataset. pd.read underscore CSV, we specify the URL, then we, for names, is equal to, we specify the column underscore names that we have above in a list, and then we would also specify NA values is equal to question mark, and following that we need the comment is equal to \tab \t, and separator we have, that is space and skip initial space is equal to true. With that setup, we can we also need to drop let's look at what the dataset looks like. Dataset.head, and let's pull just top 2 records from the dataset, and this is the dataset we have. What we can do is check how if there are any missing values in there. So dataset dot is an a dot sum, and we'll see if there are, and there are 6 missing values in the column horsepower. So as for the docs, we'll go with the docs and we'll drop these values. So dataset dot drop na, and again if we look at the dataset dot is na dot sum, now after we drop the NN values, we shouldn't see those here in horsepower. So the 6, there are no missing values now because we dropped the column, dropped the rows that had missing values in them. Next, we need to, before we do the shape conversion to tensor, let's check the shape. Dataset dot shape. So this dataset has 392 records, and after we dropped 6 records, and we have 8 columns in there. And let's look at the data types. Dataset.d types, and we have numeric columns throughout. So all of them are numeric columns. That's good. But as you'll see, the origin column is the one that will need to encode later on. So now let's move on to the next step, where we are going to convert the data frame to a tensor. And for this, we'll write dataset underscore tf is equal to tf.convert to tensor, and we'll specify the dataset, and we'll specify the data type as tf.float32. And now we can look at either the head or the tail of this dataset. So let's look at the tail. Dataset well, we already did. So that's the dataset we have now. And in this dataset, the next step what we'll do is we need to shuffle the dataset first, then we need to split it into train and test set second, and thirdly we need to split the train into features and target. So there's 3 things we need to do. So the first one is a shuffle, then we need to split into train and test sets, and then split each of these into features and target, right? That is the x and y's that we know of. And for this, here's what we are going to do. Create a shuffle dataset. Dataset underscore shuffled is equal to tf.random.shuffle, and here dataset underscore tf seed is equal to 22, so we get the same shuffling. Then we'll split it. Train underscore data test underscore data is equal to dataset underscore shuffled, and we'll put these records, so 100 onwards, those records will go in a train set, and the remaining data set underscore shuffled, remaining, that is the first 100 will go in the test set. Okay, so that's done there. Now it's time to get the x train and y train. So x train, y train is equal to train underscore data, and we'll see all the rows, and starting from the second column, we put that in the as features, and then same train data, we take all the rows and just the first column as our feature, as our target or y. And the same thing we'll do for the test set, where we'll put a test here, and again put a test in this particular case, and we add a test right here. So that's how we now have the X train, Y train, X test, and Y test ready for the next steps. Now, another part is you may have guessed by now is feature engineering or one-hot encode. Feature engineering, or here what essentially we are going to do is one-hot encode the origin column. And to do that, we are going to write a function, and this is the function def one hot origin. And the reason why we are doing the one hot encoding for this feature is it's categorical, although it's a number. And if we want to look at the exact meaning of that, let's copy this URL and paste it in the browser and see if there is a description for this. We go to the parent directory. No. So auto mpg index, I wonder. Nope. So let's see. I'm going to go down here and go to UCI ML, the repository, and in this repository go to datasets. In datasets we go to auto mpg, and that's it, was right there. So auto mpg, and if you look at the origin, it's multi-valued discrete. Doesn't say much, but we won't go into the details except knowing that that's a column which we need to one hot encode. And so this function takes in x as an input argument. The first thing we'll do is cast it as an integer. So origin is equal to tf.cast, and this is what we are going to cast, x, and we take the values in x and cast it to tf.int32. int32. And the next thing is one hot encoding using tf.1_hot. So origin underscore oh one hot is equal to tf.1_hot origin -1, 3. And I think the reason why this is 3 is because if you look at the data set, and if you look at the origin column, and if you look at the unique values in it, the unique values are 1, 2, and 3. And so what we are trying to say here is that we are starting at 0, and that may be the reason why there's -1 there. So we start with 0, 1, 2, and 3. So we have 3 classes, and therefore we have the 3 here. Now this will create the origin. So tf1 encode origin. Once we have that, we need to then concatenate the one hot encoded columns with the original data set. So to do that, here's what we'll do. X with one hot encoded columns is equal to tf.concat, and this is our original data set that is without the one hot encoded columns or the origin column. That's -1 is just indicating that the last column is not there, and it's last because if you look at the data frame, we see that origin is in fact the last column, so we can conveniently use -1 to refer to that column. Origin underscore oh, so this contains the one hot encoded 3 columns, and we specify axis is equal to 1, so we want to stack these side by side, and then we return the data frame with which now has the origin column converted to 3 one hot encoded columns. And that's our function there. Now we can use, and the reason why we are writing a function is, as you'll see later on, is when we save the model, we can pass this function to while saving the model as well. X underscore train underscore OHE is that's the train part, and then we have the test part. X underscore test underscore one hot encoded is equal to one hot underscore origin, and this takes in X train, and again the same thing for the test. So one hot origin, and this takes in X underscore test. And so we are good. I think axis. So forgot something. Oh, well, let's look at this. X train, Y train is a problem. Got multiple values for argument axis. And oh, right. So this needs to be inside of square bracket. So whenever we are concatenating, we need to put it in some sort of container like this. List should work. And now when we run this, we should get the X train and X train one hot encoded and test one hot encoded. Now, if you look at the X underscore train underscore one hot encoded dot numpy, we should see the array as like right here. So these are the values. We have 1, 4, 140, 72. So if you go back up, this is, oh, well, those are not the exact columns we have, but the order may have changed. Right, the order changed because we did shuffle them. And these are the last 3 columns that are now one hot encoded columns. Okay, so with this, the next step we need to do is normalize the values, because as you see, some of the values are much larger and some are much smaller. So next step is to normalize the data set. And so for normalizing the data set, the 2 things we are going to do is we are going to subtract the mean from each of these values and then divide that by standard deviation of that particular column. So straightforward, and here's how we will work with that. We'll create a class normalize, and this takes in tf.Module as usual, and we first create our init class, init method, init underscore underscore, that takes in self and x. And inside of this, we initialize the mean and standard deviation. So we say self dot mean is equal to tf dot math dot reduce underscore mean, and this takes in x, and axis is equal to 0. Then we have self dot standard deviation std tf dot math dot reduce underscore standard deviation x, and this is again axis is equal to 0. That's our init method. Then we define the norm method self comma x, and here to normalize the input, what we need to return is the each value subtracted from the mean. So self dot mean, we subtract the mean and then divide it by standard deviation as we as mentioned earlier. And then for unnorm, it's exactly the opposite of what we just did. And so we are in a sense bringing back the original value. Return x multiplied by self dot standard deviation, and then we add the mean to this value, self dot mean, and that's our class for performing either the normalization step or unnorm step. So to get the normalized values for x and y, we'll create 2 separate variables. Norm underscore x is equal to normalize x underscore train underscore OHE, that's one hot encoded, and norm underscore y is equal to normalize, this is going to be simply y train. And once we have initialized this, we can now use them to perform the normalization. So x underscore train underscore norm, then y underscore train underscore norm is equal to norm underscore x dot norm. So we are using this initialized variable, and we are calling this method inside of that, which is norm, and passing it the value x train underscore OHE, and what that will do is it will perform the subtraction of mean and divide by standard deviation and return the values. And the second one is norm underscore y dot norm, and again this takes in y underscore train. So that's what we have for the train, and we are going to repeat the exact same thing for test. And for that we will go back here and change the names from train to test for each of these. So test, and then again this will become test, and this will become test as well. So now what we have are what we have is a data set that was one hot encoded and subsequently normalized for the training. And so I think we are now in a position where we can start building our model. So for this, let me check once again if all of this is good, and that looks okay. Next thing is we'll build the machine learning model, and for that we'll create a heading here that says build a machine learning model. And again, that's the model we looked at earlier, y is equal to xw plus b. And for this we'll create a class which is class linear regression, and this takes in tf.Module as usual. And the first class is the first method is init underscore self, and here we define self dot build is equal to false. And the second method then is the call method def underscore call underscore self dot x self comma x. And before this method we are going to add a decorator tf dot function, and that will create the graph. So here I will initialize the model. So initialize the model parameters on the first call, and that's where we have this if statement, if not self dot build, then this is what we want. We want to randomly initialize these. A random w is equal to tf.random.uniform, and here we have shape is equal to x, shape is equal to square bracket x dot shape minus 1 comma 1. And the next thing we have is rand underscore b is equal to tf.random.uniform, and shape is equal to open close square brackets. And then we have the self, we'll declare the self dot w is equal to tf dot variable random underscore w, and self dot b is equal to tf dot variable random underscore b, and we have self dot build is equal to true. And finally then we perform the multiplication. So we have tf dot matrix multiply x comma self dot w, and then whatever is the output of this, we are going to add that to our bias, which is b. So self dot b, and we'll put the tf dot add right here. So this will calculate the value of y, and we'll return tf dot squeeze. We remove any extra dimensions, y comma axis is equal to 1, and that's the linear regression class that we have created. Linear regression is equal to linear regression. We are initializing the variable lin underscore reg using the class we have created above. Run this, and now we can pass one row to this particular model and see what output we get. And so we can say x underscore train underscore norm. So if you look at this is what's in the doc. So we have :1, so that's what we get here, and that's the same thing as saying x underscore norm, and we say we want the first row and all the columns in that first row. So it's like one instance or one record we are trying to pass in to this particular function. And so what we'll do next is put this inside of lin underscore rig, because that takes in one input argument. That's the x we are going to use, and for this we are going to save the output in the variable prediction. So that's the prediction, and we can then prediction. So you can say prediction unnormed. So prediction. Okay, let's print the prediction. So that's the prediction we have. Oh well. Oh, there's typo, no attribute u unv norm. So there's a typo there. Let's correct that, and hopefully this should work now. Okay, so this is the predicted value minus 2.08, and that's not the mileage we know of. And so what we need to do is convert that to the actual value, and we'll use unnorm for that. Prediction underscore unnorm is equal to norm underscore y dot unnorm prediction and prediction underscore unnorm dot numpy. So we get an value in the numpy array format, and we see that the output is 6.8. 6.8 is the output or the predicted miles per gallon for that particular vehicle, and we wanted to check what the actual value was. We could look at y underscore train underscore norm, or we could just look at y underscore train and look at the first value. So maybe just the index 0, and we see well, that value is 26.5, and that should be okay because we are trying to predict based on a model that has randomly initialized weight. We haven't yet trained the model, and so that's the value we have. If we try to change this to this, and still we should get the same value in the output, if that is 26.5. Now let's look at how we can define the loss function. So the loss function was a mean squared error that we looked at in the very beginning of this video. So let's type that out. Define a loss function, and what we are going to do is essentially take the squared difference between sum of squared difference between the actual value and the predicted value, between the actual and predicted value of y. So for this, we'll define the function as follows: def is equal to MSE sum of, and then we divide this by the number of samples, so mean of this. So essentially, rather than saying then divide by n, or the number of samples that we have. So this is going to be MSE underscore loss y underscore pred y. So it takes in two input arguments, and what it does return is MAC. So we could say that this is the MAC, and what it does is calculates the tf dot reduce underscore mean tf dot square. So first what we are trying to do is we are trying to take the square difference. So this is what we have y minus y pred minus y. So that's the difference in the actual and predicted value. We then square this. So we say tf dot square, and once we square these values, we take the mean of that. So we say tf dot reduce underscore mean, and that's what we are going to return from this function MAC. So we have the loss function ready. Now it's time to train and evaluate the model. So for this, we'll create another heading, which is train and evaluate the model. So for this, we'll set the batch size. Batch size is equal to 64. And then what we need to also do is use tf.data.dataset API for creating batches and shuffling of the dataset. For this, we'll create train underscore dataset is equal to tf.data.dataset dot from underscore tensor underscore slices, and here we specify a tuple. The tuple would have, so we are combining, we are kind of putting together the features and the target. X underscore train underscore norm and the y underscore train underscore norm. So these two, and then we'll perform the shuffle and batch. So train underscore data set is equal to train underscore data set dot shuffle. That's the first thing we do, and we set the buffer underscore size is equal to x underscore train dot shape 0. And so that's the shuffle part. That's done. The next thing we need to do is batch. So we say dot batch, and again here we specify the batch size as the input argument. So that's what we have for the train, and exactly same thing we need to repeat for the test dataset. So let's copy this, put this down here, and repeat this for the test. So I'm going to just rename this to test. So copy this. That's the test. That's test. Then this is test. Again, we go up here. This X test and this is Y test. And again, this is X test, and the batch size stays the same. So just to check again, we have test, tf.data from tensor slices, X test norm, Y test norm. And then we have test data. Again, here we take the test data set from above, shuffle it, and buffer size the same as X test. And then we perform the dot batch using the batch size we defined earlier. So that is all done. Now we'll perform the gradient descent method. We'll use the gradient descent to perform the kind of updating the weights, looking at the loss, and then arriving at the final predicted value. And so for this, let's give this a heading, and this is what we'll call the training loop. We are going to create a training loop here, and this is using the gradient descent method. If you're not familiar with this method, I suggest you check out the videos that on this channel in the intermediate series, where we talk about this in context of scikit-learn library. So the parameters that we need that we would be using are these. We need to set the number of epochs, and let's set that to 100. Learning rate, let's set that to 0.01. Train underscore losses and test underscore losses. We can capture these and put them in this list. So we'll initialize these as empty lists, And these are important because later on we can create nice visualizations or plots to see how both of these decrease, and that kind of tells us if our model could be overfitting or underfitting. Again, for that you would use a validation dataset, which we do not have here, but we just have the trained dataset. We did extensive we did look at that extensively in the previous video for overfit and underfit. For now, let's proceed with this, and the loop will start out like this: for epoch in range epochs, and within this first thing we'll need to do is capture the loss for the batches, because we'll be working in batches. So the first we have is batch losses for train, and then we have batch losses for the test. So these two are important, and we'll combine these two later on and put them in the train losses and test losses that we have initialized just above. Next thing we need to do is iterate over the training data, right? And then we need to iterate over the test data. So this is what we need to do, and then we need to kind of update our training loss. So calculate the overall calculate, instead of saying calculate, we'll say update the overall training loss, training and testing, train test loss, or just say losses. That should be good. Update overall losses. And so in the first case here, there's additional thing we need to do is update weights and biases, update the weights and bias using gradients. Okay, so the very first thing we need to do is start out with a for loop. For x underscore batch, y underscore batch is in train underscore dataset, and here what we are going to do is create a gradient tape. So with tf.gradient tape as tape colon, and here we'll use the linear underscore reg, and this is going to will input the batch, the features that we have in the batch, and that will output us the predicted values, which we'll put in this variable, the predicted value y pred batch. So we have the predicted values now. Now we'll use these predicted values to calculate our losses, and the way we calculate the loss is using the same function we had above. So we use the MAC underscore loss, and here we specify y underscore pred underscore batch comma y underscore batch. So we input these two to the method we just described here. That will calculate the error and will return the error, and we'll put that error in this variable batch underscore loss. So the tf.gradient is recording all of this, and so that's what we'll use shortly. Once this is done, what we can then do is calculate the gradients. And so let's put a small note here: calculate gradients, and gradients I will put the variable name as grads is equal to tape dot, and this is automatic. We do not have to worry about how to calculate the gradients, which is a little nice. Gradient, and this will take in the loss that we have calculated and the lin reg dot variables. Now if you're wondering what these are, lin underscore, we will come to that in a moment after we write out this entire loop. Next we have for g comma v in zip grads comma lin underscore reg dot variables, and from this, so there's a typo, grads, okay, gradients, and Now what we need to do is subtract the value which is rate learning rate times g. So we want to subtract this value from all the existing values for weights and the bias, and so we say v dot assign sub. So sub for subtract, and that's what the subtract will do. And after this, then what we'll get, so below this, what we can then write is or we can append the batch underscore losses underscore train, append to that the batch underscore loss. All right, so with this, what we can do is I'm going to put a break right here for this break. And so once we have this done, this is outside of this, and so this should break right here. And the reason for this is want to take a look at what's inside of each of these. So what we can do is we can write a bunch of print statements to check what's actually happening. And so let's print the first one. Here we have x underscore batch, and let's say x underscore batch. So that will print what's in our batch. And when we look at this, so let's stop this again. Oh, my mistake. And number of epochs, we'll set this to 1 for now, and we can change it later on. So in the first case, here's what we have in our batch, which is a tensor that we see here. If you want to take a look at the shape of the x underscore batch, we can do that. So x underscore batch dot get underscore shape. This shape is at 64 by 9, and that's what we would expect because we have a batch size of 64. So 64 records in this particular case. So that's good. So we know we can. So if we print x underscore batch dot get underscore shape, and this that's the exact same thing that we have down here, where we have the shape 64 by 9, and I'm going to copy this and paste it right here so we see that in the output. And next what we have is the output of this y underscore predicted. So let's print that out as well. Print, why don't we copy this and we print this with y underscore batch instead of x underscore batch. And so now when we run, and this again needs to be y underscore batch. So let's look at this, and these are the predicted values. These are of course normalized values, and therefore they do not look like miles per gallon, but that's what we have. So far so good. We are good with these. And then the next thing is the batch loss. So this again is going to be the difference between the actual values and the predicted values. And so this is batch underscore loss. So let's put that there, and we don't need this sentence here. And the last line, this is the loss we have, batch loss. And with this, then that batch loss is then used as an input here, along with this linear regression dot variables. Now if we want to look at what's in that, we can print that. We can look at this as follows: print linear underscore reg dot variables, and we say comma linear underscore reg dot variables. And when we run this, let's see what we get. So here's what we have. We have two things. So let's look at the type of this. And I'm going to comment this out just because it's just an array of, we know already what's in there. So what we can do here is print the type, not this one. We need this. So copy this and paste it again here and look at the type. So if we look at the type of this particular output of this, let's look at the type of this. And so this type, it's it's a tuple. Yeah, right. It's a tuple, and this tuple has two values in it. This is the first value, and then this is the second value. So the first value is just a single numpy, some single value, and that would be the bias, the B, and then we have this array which is going to be our weights. So what we are going to do next is update this bias and update these weights in each of these iterations based on the gradient that is calculated. So next what we get down here are the gradients. So if we put this here, and if you look at the type grads, so let's do where this grads, and again if we remove this and type grads, and we look at the grads itself, gradients, and then this again would be gradients. Look at these, we should see the same shape of values. So here we have grads. Again, this is a tuple and it has two values. This is the first gradient, that's the gradient, and then these are the other values for the gradients. Now when we perform this calculation, learning rate into gradient, let's do that. So I'm going to print within quotation learning rate. We know that the learning rate is 0.01 quotations, and we put this here. So that's the learning rate we have, and let's go through just one iteration of it, and I'll put a break there. Now when we look at the values of, we also need to look at the values of G and V. So let's print those out. Print G, what G has, and then we'll print the value for V, and let's look at what that has. And this value of G and V is, this is right, this is the V before, and so we are going to put just a note there that that's the V that is before we perform any sort of subtraction, and this is the V that is now after we perform the subtraction. And let's change the before to after, and now when we run this, here's what we get. This we were up to here, we saw this was a tuple for gradients, then we saw that these were the values we got from there, and now the G that we are pulling is one value at a time, and the first value we are pulling is the minus 0.017, and if we look in this case, this is the first value, minus 0.017. That's the first value from G, and then the V again has the first value from this one, which is minus 0.00343. So that's the minus 0.00343. And then this is the calculation that is taking place with the learning rate times the G. And so learning rate that we have is 0.01. So we multiply that by this value. And so we get additional zeros in front here. And so that's the value we have, 0.00174. That's the learning rate times G. And then we are going to subtract this value from this value. And so if we do that in the cell below, let's try and do that. So I'm going to put this value right here, and we are going to subtract this calculated value from that. Let's see, We subtract, it's a negative value, like so. And when we perform the subtraction, we get minus 0.00326, and that's what we have, minus 0.00326. So that's how the gradients calculated using the gradient tape can be used to update the weights and the biases in different iterations. So that was the first iteration. So let's create a print, and we'll put a line here, that just so that we know that that's where the iteration ended, times 30, and this will run through all the iterations. So let's run this loop for gradients, and what we are interested in, just trying to find out what calculations are going on. Let's look at the last one. In the last one, what we have is the gradients. Where is it? So these are the values calculated for the learning rate, and those are calculated, of course, based on the value of g. So let's look at the value of g, which is this tensor right here, and the last value we have is 0.12078, and times 0.01 we get 0.012078, and that's that value. We multiply, so that's the learning rate times g, and then what we are going to do is subtract that value from the value for the v before. So it's this value. So if we take this value and put this right here, and then take our gradient multiplied value and put that value right here, run that, and we see that 0.5213, and that's the value we have, 0.5213. So that's how the gradients are calculated. I'm hoping this explanation was kind of helpful to understand actually what's going on in this particular block of code. So we can now go ahead and just comment those out, because we don't need to see all the prints in the output. So I'm going to do that. And so this is what we had to do for our test, iterating over the test data. We don't need to do that over the, sorry, we did that for the train data. We don't need to do that for the test data set. So let's go ahead and remove this break as well, or maybe just comment that out, comment out the break. And if we scroll up, yep, everything else looks okay. Once we are done running through the train, we can now write a similar loop for the test data set without the need for doing any gradient updates. For x underscore batch, comma y underscore batch, in test underscore data set, y underscore pred underscore batch is equal to linear underscore reg x underscore batch, and then that's the, we are calculating the predicted values, and then we can get the loss, batch loss is equal to mac underscore loss y underscore pred underscore batch comma y underscore batch. So we get the loss there, and we can append this loss to the empty list we had above, batch underscore losses dot test dot append batch underscore loss, and that's all we have for the test data. There's an error, so wondering why that is the case. Batch underscore loss, oh, that's forgot to add a test there. So batch, we need to add it to the list, that is the test list. After this, we need to update or keep track of epoch level. So this is now epoch level, losses that we are going to keep track of. And so we say train underscore loss is equal to tf.reduce underscore mean, and for this we are going to the batch underscore losses underscore train, that's for the training data, and then test underscore loss is equal to tf.reduce underscore mean batch underscore losses underscore test. So that's for the test data set, and then train underscore losses dot append train underscore loss. So we append this, and then test underscore losses dot append test underscore loss. And you may be seeing some lag here on the screen. Next, what we need to do is the following. We want to print the output not for every single epoch, but every let's say every 10 epochs or so. So here's the if condition for that. If epoch percent 10 is equal to 0, then what we want to do is print the following. Print f, and within quotes, mean squared error for step, and here we say epoch, close curly braces, again open curly braces, and here we say train underscore loss dot numpy, and then we have 0.3f, closing curly braces, and so this is what will get printed every 10 epochs. So the mean squared error for the steps that we have. Output final losses, print f back n final train loss, train underscore loss colon 0.3f, and close the curly braces, and finally the test losses. So copy that and paste it right. Copy that again, copy that, paste it right here, and this is the test losses, and change this to test loss. Now when we run this, hopefully we should get the mean squared error for each epoch, except there is an error, and I see what the error is. There's a typo. This we don't need that 2 times, so let's run that again, and we have the just one iteration. That's because we did set this to 1. Now change that to 100, run this again, and run this again. So now we should see, here is the loss, and as you can see, the loss is starts out at 0.2, and then it continues to decrease. It falls as low as just 0.17. That does not make much sense because the initial loss should have been much higher. What I'm going to do now is run clear, restart, and run all. That's because if the list already has the previous losses, maybe that's causing these to calculate the lower values. Let's run this again and see what we get in the output. The initial loss should be high. Okay, now this makes sense. The initial loss is around 2.87, and then we have this go down to 0.16 with the final test loss as 0.157. And with this information, we can now create our plots to visualize the losses. So I'll create a heading, plot the losses, and here we'll use the matplotlib library, matplotlib.rc params, and we'll set the figure size. There are different ways to do this. Here we'll follow the method that's in the docs. Fig size, and here we say is equal to open close square brackets, so the figure is 9 by 6, and we say plt.plot range epochs, and train underscore losses, label is equal to training loss, and then we have same thing for the overlay plot with the same thing and same number of epochs. And here we have test underscore losses, and label this time is going to be testing loss. And we can add the labels plt.x x label. So plt.x label is epoch, and plt.y label is mean squared error loss, and plt.legend, and then we have plt.title, that is MSE loss versus training iterations. Let's run this, and we see a nice plot where as the training loss decreases, so does the test loss, and after around 20 epochs there seems to be lesser and lesser improvement in the model accuracy. As we can see, the training loss sort of plateaus there. Now it's time to save the model, and so let's create a heading, save, and we'll also reload the model to see how it works. Now for saving the model, we'll create what is called as an export module, and what it does is it does two things. It takes in the raw data, and this also, and it performs the operations such as feature extraction, normalization, prediction, and unnormalization. So it does all of these things. And so this is going to be a new class export module, that again takes in tf.Module as an input. And as always, we have the first method inside of this, which is init method, and this takes in self model extract underscore features norm x norm y, and then we initialize the pre and post processing functions. So initialize pre and post processing functions. Self.model is equal to model, and then self.extract underscore features is equal to extract underscore features. I wonder why we have that red squiggly line there. I'm going to do a backspace, run this, and still we have that. Never mind. If it creates a problem, we'll come back and take a look at it later. Next, self dot norm underscore x is equal to norm underscore x. Self dot norm underscore y is equal to norm underscore y. And then we create the next function def. That is def underscore call. That underscore call that takes in self and x. And for this function, we are going to add a decorator on top of it. So let's put a colon there and add a decorator up front. It says @tf.function, and that has these parameters: input underscores signature is equal to tf.tensor spec shape is equal to none comma none, and then we have the data type. D type is equal to tf.float32. Down here inside of the function, what we'll do is run the export module on Run the experiment for new data points. X is equal to self dot extract underscore features X. That's the X. Then we have the X is equal to self dot norm underscore X dot norm X. So this will perform the normalization, and then we have Y is equal to self dot model X. So that's the predicted Y, and then Y is equal to self dot norm underscore Y dot unnorm Y. So the predicted Y's, we unnorm that, and then that's the Y we get, and we'll return that value. Return the Y. So here is the function we have created. Now what we can do is use it. Linear underscore, we created, sorry, what I meant is we created the class, and now we are going to initialize that class. Linear underscore reg underscore export is equal to export module, and this has model is equal to linear underscore regression, comma, next we have extract underscore features is equal to one hot origin. That's what we created earlier. And then we have norm underscore x is equal to norm underscore x, norm underscore y is equal to norm underscore y is equal to norm underscore y. And this is what we have created. Initialize the export module, and next we can again continue with this. Import temp file, import os models is equal to temp file dot mkdtemp. Then we create a path. Save underscore path is equal to os dot path dot join models, comma, linear underscore reg underscore export, and then tf dot saved underscore model dot save linear underscore reg underscore export, comma, save underscore path. So that should save the model unless there is an error. So let's figure out. Name models is not defined, and that's because missed the s there. So this will save the model, and we can now reload it as below. So here we are reloading the model, and here we are saving the model. Save model, and here we say reload model. And for reloading, we say lin underscore reg underscore loaded is equal to tf dot saved underscore model save underscore path, and then we have test underscore spreads is equal to lin underscore reg underscore loaded x underscore test, and we have test underscore spreads is a test underscore spread square bracket colon 10 dot numpy. So we are looking at just the 10 values, predicted values. By mistake, there should be a G instead of a Q, and still an error. RE lin underscore reg loaded is equal to tf dot saved model. Oh, forgot to type dot load. Saved model dot load, and here are the values that we have in that are the predictions for miles per gallon for this particular X test that we have. And we could also look at the values. So if we look at y underscore test, we get the 10 values. Again, say dot numpy, and run this. Let's see what value we have. The values that are, instead of 28, we have 18. The last value is 27. 25. We got 27. Then we have 15 and so on. So this is how we have the values for the predicted values for the test dataset. And that is the end of this video. If you have any comments or suggestions, please do let me know in the comment section below. I hope in this video you got intuition on how to use the core TensorFlow API to create a basic linear regression model. And here we use the auto MPG dataset to predict the fuel efficiency of vehicles. Hope to see you all in the next video. Please like, share, and subscribe. It helps me stay motivated to create more interesting content for you all. Thank you.